Good morning, everyone. Myself, Mohit Bansal, and in this video series, we will start the gas cycle refrigeration. And the very first cycle which comes in the gas cycle refrigeration, that is Bell-Coleman cycle. So, to know in depth of the Bell-Coleman cycle, we will start with a numerical problem. So, in this numerical problem, it is saying an air refrigerator working on Bell-Coleman cycle takes air into compressor at 1 bar and 268 Kelvin. So these are the input parameters for the compressor. It is compressed in the compressor to 5 bar and then cooled to 298 Kelvin in the cooler at the same pressure. So we all know that that's heat exchange process in the heat exchanger is happening at the constant pressure. That's why it is saying at the same pressure. It is further expanded in the expander to 1 bar and discharged to take the cooling load. The isentropic efficiencies of compressor and expander are 85% and 90% respectively. So first of all, we'll write down the things which are given to us. The very first thing which is saying is, okay, so we'll draw the TS diagram for the cycle. So we are starting with this 1 to 2 compression process. Then there seems to be heat rejection in the cooler. And then this is expander. And this is the refrigeration effect, which we will see in the refrigerator. So I'll name the processes 1, 2, 3, 4. 1 is the entry to the compressor, and 2 is the exit of the compressor and entrance to the cooler. 3 is the exit of the cooler and entry to the expander. 4 is the exit of the expander and entry inside the refrigerator. So these are the processes. So in this part 4 to 1, we will get our refrigeration effect or cooling effect. And 2 to 3, this is heat rejection at the higher temperature. So again, writing down the things. So T1, which is given to us as 268 Kelvin and pressure P1 is 1 bar. So we all know that in the TS diagram, the pressure lines are of the diverging nature. So I'm just drawing this with another color. So this is the pressure P1, which is equal to 1 bar. And this is the pressure line P2, that is 5 bar. 5 bar. So T1, P1 and pressure P2 is 5 bar. And then the same thing is written like it is cooled to 298. Now this part is very important, that after cooling the temperature T3 is 298 Kelvin. 298 Kelvin, which is happening in the cooler, and then discharged to take the cooling load. And one very important part is that the isentropic efficiencies of the compressor and expander are 85% and 90% respectively. So in the compressor, the isentropic efficiency is like 85%, and for the turbine, it is 90%. So the diagram still it is not completed, because if the efficiencies or the thermal efficiency or isentropic efficiencies of compressor and turbine would have not given, then this diagram would be perfect. But now the compressor and turbine are shown with an isentropic efficiency. So we have to show the process of compression, and this compression process is polytropic compression with friction, because you can clearly observe in this diagram, I'm moving from 1 to 2 in the right side. That means entropy is increasing. So it is showing polytropic compression with friction. So we can move in this side on the left side like 1 to 2 double dash, but this will not be the case, because polytropic compression with cooling can be shown with this process. So I am starting this thing. So our new point will be 1 to 2 dash. So this is the thing 2 dash. So this is polytropic compression, and then the for turbine it would be somewhere here. This point will be 4 dash. So our actual cycle will be 1, 2 dash, 3, 4 dash, and 1. So this numerical problem is of the closed Bell-Coleman cycle or dense air cycle. In this the working medium is the air, and it is moving in the closed cycle. So this is our actual cycle. So first of all, if any of the problem comes based on Bell-Coleman cycle, we have to find out the unknown temperatures. Like in this diagram, we have seen that T1 is given to us and T3 is given to us. Generally, these 2 points or these 2 temperatures are only fixed temperatures, because T1 represents the temperature of the cabin or the refrigerator, and T3 represents the ambient temperature. So generally in any of the problem of Bell-Coleman cycle, these 2 temperatures are given, and these 2 are the fixed temperatures also. So very first part is to calculate this temperature T2, which is on this reversible adiabatic line, isentropic line. So we will start our problem to find out this unknown temperatures T2, T2 dash, T4, T4 dash, and then we will find out the which is asked to us, like refrigeration capacity of the system if the air circulated is 40 kg per minute. So I'll write down the mass of air which is given to us. That is, mass of air is equal to 40 kg per minute. And then the power required for the compressor and the COP of the system. So very first thing in the process 1 to 2, which is the reversible adiabatic compression process, we will use this thermodynamic relation T2 by T1 is equal to P2 by P1 raised to power gamma minus 1 by gamma. Sometimes in place of gamma, this it shows polytropic compression with the relation PV raised to power n equal to constant. Now it is not given to us, so we'll use this thermodynamic relation, and we will find out the temperature at the exit of the compressor T2. So that will be T2 equal to T1 into this P2 by P1, that is 5 by 1 raised to power 1.4 minus 1 divided by 1.4. T1 is given to us, that is 268 Kelvin. So on solving, I've already solved this thing. So T2 comes to us as 424.46 Kelvin. So you can easily calculate this thing. Okay. Now, the cycle is not 2, means we have the actual cycle as at T2 dash. So we have to find out, this is the temperature T2, but we are not very much concerned with this temperature. We have to find out this temperature of the actual cycle, that is T2 dash. So for that, we will use the isentropic efficiency of the compressor, and isentropic efficiency of the compressor is given as isentropic temperature rise divided by actual temperature rise. So I am writing this isentropic temperature rise in compressor to the actual temperature rise in the compressor. Sometimes when we have to write this relation, we generally miscalculate the things, and sometimes we confuse whether we have to write it like isentropic term on the up or in the down. So do remember this thing in while solving the or while writing the isentropic efficiency of the compressor, we have to take this isentropic term or temperature rise in the numerator and the actual temperature rise in the denominator. So that will be T2 minus T1 upon T2 dash minus T1. That will be the isentropic efficiency of the compressor. And in this relation, we do have this eta C, that is 0.85. We do have this T2, we have just calculated T2, T424.46. T1 is also available to us, that is 268 Kelvin. And T2 dash is the only unknown. So I'm writing down the temperatures, 424.46 minus T1 is 268 upon T2 dash minus 268. So on solving this thing, our T2 dash comes out to be just cross multiplying this isentropic efficiency, which is 0.85. I'm just writing it down. So it can be easily calculated, and on solving this T2 dash, it will be more than this T2, and it is coming as 452 Kelvin. 452 Kelvin. So out of the complete cycle, we have just calculated the actual temperature rise of this cycle, which is happening from 1 to 2 dash. So I'm writing this on the y-axis also, T2 dash. So now the thing is, we have to find out the exit temperature of the expander. So likewise in the process 1 to 2, we will see, I'm just changing this thing. Yes. So now we will start with the process 3 to 4 and use the thermodynamic relation for the same. T3 by T4 is equal to P3 by P4 raised to power gamma minus 1 by gamma. P3 and P2 are same. So P3 and P2 both are the same thing. And P1 and P4, they both are same. So that will be 5 raised to power gamma minus 1 upon gamma. So we can easily find out this T4. T4 on the solving this thing, it comes out to be 188.15 Kelvin. 188.15 Kelvin. Now the actual cycle is not 4, rather it is 4 dash. So we have to find out this T4 dash. For T4 dash in the numerical problem, it has given to us that the isentropic efficiency of the turbine is 0.90. So likewise, we have written the isentropic efficiency of the compressor. Now we have to write down the isentropic efficiency of the expander. So the expander, for the expander, we will write it as actual temperature drop. Actual temperature drop in the expander. Actual temperature drop in the expander to the isentropic temperature drop. Isentropic temperature drop in the expander. So you can easily see this thing. In the case of compressor, it is the isentropic term is on the numerator, and for the isentropic efficiency of the turbine or the expander, the isentropic temperature term is on the denominator. So it is given to us 0.90 isentropic efficiency. Actual temperature drop is T3 minus T4 dash, the actual temperature of the cycle, and isentropic temperature drop. Isentropic temperature drop will be T3 minus T4. So by writing down this T3, which is given to us in the question, it is 298 Kelvin or 25 degrees Celsius, and T4 we have just calculated it as 188.15. So our T4 dash of the actual cycle comes out to be 199.14 Kelvin. So these are the unknown temperatures, which are very much essential to find out the cooling load and the work output of the compressor. And for the COP, these are very much essential. So now we have to just see, but we have to calculate. It is in the very first part, it is asking refrigeration capacity of the system if the air circulated is 40 kg per minute. So mass of the air circulated. We all know that in the gas cycle or in the Bell-Coleman cycle, which is also known as Joule cycle or reverse Brayton cycle, the fluid which is used for the refrigeration purpose, it is air. And in this question, it is given to us that the mass flow rate of the air circulated is 40 kg per minute. And it is asking that to calculate the refrigeration capacity. Refrigeration capacity. So refrigeration capacity is given as mass flow rate of the air into the refrigeration effect. So mass flow rate of the air is given to us, and this refrigeration effect is in the process 4-1. In the actual cycle, the refrigeration or the cooling effect which we are able to get in the refrigerator is happening in this 4-1. So what we will write, m dot a into Cp T1 minus T4 dash. So this will give us as the refrigeration capacity. It could be in kilojoule per second or kilojoule per minute. So first of all, we will calculate it in kilojoule per minute, and then we will reframe it in the kilowatt term or kilojoule per second. So 40 kilogram per minute, and this is specific heat of the air at constant pressure, which is 1.005 kilojoule per kg Kelvin, and T1 is given to us in the question, which is 268 Kelvin, and T4 dash, which we have just calculated, it is 199.14 Kelvin. So on solving this thing, refrigeration capacity, it comes out to be 2768 kilojoule per minute. But generally, we are much more concerned to represent this refrigeration capacity in terms of kilojoule per second. So when we divide this thing, 2768 by 60, it comes out to be 46.13 kilowatt. That is the refrigeration capacity. So this is our answer for the first question. Then the second thing is it is asking from us power required for the compressor. Power required. So we all know in the Bell-Coleman cycle, as per our this representation, the compressor is from 1 to 2. That is the ideal cycle, isentropic compression 1 to 2. But in the actual cycle, the compression process is happening from 1 to 2 dash. So the power required, that will be equal to mass flow rate of the air. We will represent the same thing in kilowatt or in kilojoule per minute. So mass of air into Cp into T2 dash minus T1. Mass of air, it is 40 kilogram per minute into specific heat of air into T2 dash. We have calculated in the last slide. T2 dash was 452 Kelvin. 452 minus T1 is 268. That is, it comes out to be 7396.8 kilojoule per minute. And when we will divide this guy with the 7396.8 divided by 60, it comes out to be 123.28 kilojoule per second. So that will be the power required for the compressor. Actually, this term is the power or the net power that will be work of the compressor minus work of the turbine. So in the last slide, we have calculated this work of the compressor, which is happening in the 1 to 2 dash. So it comes out to be 123.28 123.28 kilojoule per second. Likewise, for the process of the expander, we have to find out this work of the turbine, and in the same manner we will find out this mass flow rate of the air into Cp into T3 minus T4 dash. So the work of the turbine, it comes out to be 66.24 kilojoule per second, and the net power which is required for the compressor to drive, it comes out to be 56.99 kilowatt. So that will be our answer to the second question. Power required for the compressor to drive this unit, it comes out to be 56.99 kilowatt. Now the third part. In the third question, it is asking to us COP of the system. So we are very much aware this COP is represented as the ratio of refrigeration capacity to the power, and both of them are represented in kilowatt because COP is unitless. So do remember this thing, when we will take this refrigeration effect, that has to be replaced with this work term, that will be kilojoule per kg. So this in this term we have taken the refrigeration capacity to the power. So refrigeration capacity, we have just calculated it as 46.13 to the 56.99, and on solving this COP comes out to be 0.81. So that completes our question or numerical on the Bell-Coleman cycle. So in this thing, we have taken all the parameters and find out the unknown temperatures, then refrigeration capacity, power required to drive the compressor. So this power is this relation which we have just written, it is work of the compressor basically. This is the work of compressor. So power is WC minus WT. So these are the references. Thank you, everyone.